Well, hi guys. Today I'm going to do a Taylor polynomial for a function that is not even defined at 0, so we're not going to be able to do a Maclaurin polynomial. And then I want to show you a couple examples of why Taylor polynomials are useful. Before we do this, just again review from yesterday. Our formula for a Taylor polynomial is a polynomial with all these pieces of information going out as far as you're told to go. And you need, of course, the function value at the center, and then you need lots of derivatives at the center until you get to the required degree or the required number of terms. In condensed form, it's this summation. And then the Maclaurin series we did yesterday, that one is the Taylor polynomial where everything's centered at 0. And of course, we talked about yesterday, we have these three main ones that you really should know, because if you know those three, you can write a whole bunch of other ones without going through all of the painful process of derivatives. So there we go. We're going to start with a function y equals the natural log of x. And the function natural log of x, of course, if we were to graph this thingy, natural log of x is not even defined at 0, so we can't use a Maclaurin polynomial. Of course, it goes through 1, 0, and then just sort of levels off like this. Doesn't really level off because it continues to approach infinity. But I can't write a Maclaurin polynomial for natural log of x because it's not even defined at 0. See, polynomials do a horrible job of emulating vertical asymptotes. So they just can't go straight up and down. So I can't write a Taylor polynomial there. So what I'm going to do here is I'm going to write this polynomial centered elsewhere. Let's center this one at x equals 1. So let's write out the general form for this. And let's be more specific. Let's write, the first 3 terms. Now this is different than what you did in class yesterday. Yesterday in class we said write out to the 3rd degree or the 4th degree. But let's just write the first 3 terms. So that would be, our Taylor polynomial would look like this. F of 1 plus f prime of 1 times x minus 1 plus f double prime of 1 times x minus 1 squared. That's over 2 factorial. That's the first 3 terms. So I need to get these pieces of information. So since my f of x is natural log of x, let's get some information here. What is f of 1? Well, f of 1 is the natural log of 1. That is 0. Well, that's not a very useful term. I might want to go one further past that, but it's 0. Now, to get the other pieces of information, I need to get some derivatives. So let's find f prime of x. Of course, the derivative of natural log of x is 1 over x. So f prime of 1 is just 1. So that goes right there. And then now let's get the second derivative. Of course, 1 over x is x to the negative 1. So my second derivative is negative 1 times x to the negative 2, which is the same thing as negative 1 over x squared. Okay, so f double prime at 1 is, well, negative 1. So that's going to be minus 1 over 2 factorial times x minus 1 squared. Let's get another term. I'm unhappy with this because the first term worked out to be 0. Let's go one further. So let's have the first 3 non-zero terms. Haha. So I have 2 non-zero terms. So now let's get the next one. I'm going to need the third derivative because the next term would be, of course, f triple prime of 1 over 3 factorial times x minus 1 cubed. That would be the next term. So f triple prime equals 2x to the negative 3. That's from this derivative right here. The negative 2 down makes it positive. So that's 2 over x cubed. And so f triple prime at 1 is 2. So let's see what we have so far. Our polynomial so far is x minus 1 minus x minus 1 squared over 2. And what would the next term be? Our next term is plus 2 over 6, 3 factorial 6. So I'm just going to call that 1/3. That's going to be x minus 1 cubed over 3. This looks like a pattern. And there is a pattern. As a matter of fact, if we were to keep going, the next term would be minus, it's alternating, x minus 1 to the 4th over 4. And then the next one would be plus x minus 1 to the 5th over 5. But I'm getting too far here. So there is the answer to my question. The first three terms for natural log of x centered at 1. Why centered at 1? Because we couldn't center it at 0. All right, so why is this useful? Well, this is a Taylor polynomial that defines natural log. And as a matter of fact, we're going to find out that the natural log of x is equal to a series. And that series is alternating. And the terms go x minus 1 to the n power. This is all over, just n, not n factorial. And we're going to start this from 1 to infinity. So if we plug in 1, we have a x minus 1 over 1. And then plug in 2, we get a negative x minus 1 squared over 2. And then plus x minus 1 cubed over 3. Now the College Board does not say that you have to know this one, but this is very useful to know. So I'm going to require you guys to know this one, and you're going to be happy that I did. And it keeps going, you know, dot, 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 all the way out to that general term, x minus 1 to the n over n with your alternating part to it. Okay, now this one, however, we're going to find out in a couple days. We can't just find the natural log of 7 from this. You see, if we go back to this graph, natural log of x from our center, 1 unit away from our center, we had a vertical asymptote. That means that we are only going to be able to also go 1 unit to the right. And as a matter of fact, we're going to find out that we can go all the way out to 2. So this Taylor polynomial is only good from 0 to 2. And it's called an interval of convergence. So this, you're going to find out in your book that this is only valid from 0 to 2. Of course, I can't include 0 because that's got the vertical asymptote. I can include 2 because if you plug in 2 for x, let's see what kind of series we get here. If you plug in 2 for x, you're going to get 1 to the n over n. And what do we get here? We get the alternating harmonic series. Well, this is interesting because I have now figured out what the alternating harmonic series converges to. Earlier, we just said that, well, I might have told a couple of classes what it actually converges to. But the alternating harmonic series, let's do a little caret there because I forgot to do harmonic. The alternating harmonic series converges to the natural log of 2. And here's why. If I were to plug 2 into this expansion, I would get 2 minus 1 minus 2 minus 1 squared over 2 plus 2 minus 1 cubed over 3. And then minus 2 minus 1 to the 4th over 4. And I would keep going. Let's look at these terms. This is 1 minus a half plus a third minus a fourth, and on and on and on. And that's what the natural log of 2 equals. So the alternating harmonic series converges, and now we know what value it converges to. But now let's estimate this. What is the natural log of 2? Why is this Taylor polynomial helpful? Well, I can say that the natural log of 2 is approximately equal to the first few terms. And I'm going to stop at some point. Let's do 1 minus a half plus a third minus a fourth. So I'm going to say this is approximately equal to this. Now, obviously, I've left off some other things, but we know the error in the alternating series test. Let's figure out what this works out to be. Let's do all of these into twelfths. So this is 12 twelfths minus 6 twelfths plus 4 twelfths minus 3 twelfths. 12 minus 6 is 6, plus 4 is 10, minus 3 is 7 twelfths. Now let's ask our calculator what that is. Now I know that's not right, but I can give us an error statement. I know that my error is less than the next term that I omitted, which is 1/5. So I know for a fact that the natural log of 2 is approximated by 7 twelfths, but I know that this answer, whatever it is on the calculator, will be no more than 0.2 away from the actual answer. Let's go take a look at it and see. got my calculator here. I'm going to ask my calculator what the decimal value for 7/12 is. 0.5833 repeating. Now let's ask the calculator what the natural log of 2 is. 0.693. Now our error was 1/5, and 1/5 is 0.2, so I was at the most 0.2 away, and if you were to add 0.2 to this, you'd get 0.78. So the natural log of 2 was actually within that boundary. So I used the first 4 terms and I approximated the natural log. If I wanted to get a closer approximation, I would just keep adding more terms there. So that's one of the reasons that Taylor polynomials are used for, is to actually approximate things that we don't know in our head. All right, let's do another example of approximation here. Let's go to, let's find out what the square root of e is, or at least let's approximate the square root of e. So let's approximate the square root of e, which by the way means e to the 1/2 power. Now in class we should know from yesterday that e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus ... This means that I can find e to anything with that. We're going to find out that e to the x converges, or this series, this Taylor polynomial, converges to e to the x for all values. So unlike natural log, I could actually find e to the 17th power here with this Taylor polynomial. So that means that e to the 1/2 should be 1 plus 1/2 plus 1/2 squared over 2 factorial plus 1/2 cubed over 3 factorial plus 1/2 to the 4th over 4 factorial plus ... 1/2 to the n over n factorial. Now I got to stop this at some point, so let's just use the first 4 terms here. So let's say that e to the 1/2 is approximately equal to 1 plus 1/2 plus 1/2 squared is a 4th divided by 2 is an 1/8, and 1/2 cubed is an 1/8 divided by 6 is 1/48. Let's stop there. Now, if I'm just going to go to my calculator and ask my calculator what this is, and let's see how close that is. Now, I know that's not exactly right, but let's see how close the approximation is. So back to my calculator, I'm going to do 1 plus 1/2. Let me come back here and make sure I've got the right one. Plus an 1/8 plus a 48th, right? Leave that up there. Plus 1/8 plus 1/48. Now that's 1.645833. Let's find out what the square root of e is. So let's see, where is my square root button on this old thing? Square root of e. 1.64. Boy, look how close that is. So Taylor polynomials are useful to approximate what's called transcendental functions. It's even going to get cooler with sine and cosine, especially if we stay closer and closer to our center. But you'll see that in class more often. So anyway, that's an example of a Taylor polynomial centered elsewhere. We did natural log because we couldn't center it at 1. I mean, we couldn't center it at 0, so we had to center it at 1. So you notice how these terms have parentheses like x minus 1 and x minus 1 squared over 2. So you've got to know how to use that formula as well. All right, well, I will see you guys tomorrow.